Complexity has a structure, a very complicated structure. It can be unpredictable, but it's not necessarily random. We need to start out talking about probability, because even though big data is not necessarily random, nor does it even need to contain randomness, there are still really good reasons to talk about probability. We can interpret it as a measure of how likely an event is to occur, or if there's no randomness, it can be interpreted as a measure of how believable a result is. So random or not, we need probability. So let's review. A sample space is a set of all possible outcomes of a process. For now, we're only going to look at finite sample spaces. For example, a single coin toss can be heads or tails. Six-sided die has a sample space of the 6 different outcomes. An event is a subset of the sample space. For example, A equals the subset heads is the event of getting a heads while flipping a coin. 2, 4, 6 is the event of rolling an even number with a die. And the probability of an event A occurring is denoted probability of A, PR of A. And to compute it, we count the number of occurrences of event A in n trials, and then we let the number of trials go to infinity, and that gives us our probability. Now this is one way of interpreting probability, but it can be defined and interpreted in many ways. Limit of frequencies, we just saw that. Likelihood of an event A occurring. A concept related to information, which will eventually be our focus. Interpretations, though, don't change basic results. If the one toss of a fair coin, the probability of heads is a half, then that's pretty much true regardless of how we interpret the probabilities. Same thing with the roll of a fair die. Now variables can be associated with a process. The sample space is the set of all possible outcomes, and a variable is associated with a process if it can attain any value in the sample space, and in any trial of the process the value of this variable is in S. For example, S could be the set of clock outcomes, and then X could be valid clock times. Now if the process is random, then we have a random variable, but the same idea, we can be associated with a set, which means, for instance, if it's heads or tails, X is either heads or tails. If it's associated, X is associated with 1, 0, then either X is 1 or X is 0. Notice the use of the capital letter here. So our variables are capital letters. A trial is an instance in which random variable X takes an outcome in the sample space. A process or experiment, for example, flipping a fair coin. A trial would be where we got a heads or a tails. Now we tend to index the outcomes in the sample space. This is a finite sample space, so we can just list the outcomes, and there's capital M of them. The probability then of a random variable X being assigned an outcome O sub j is several different notations. For example, the toss of a fair coin, S is tails or heads, which we can say is outcome 0 or outcome 1. Until the probability that X is heads, it's the probability that X is outcome 1, the probability that X is 1 corresponding to outcome 1, or P sub 1, and in all cases we get a half. Now if we have a variable associated with a set S, then the probability has to be greater than or equal to 0, and the sum of the probabilities over all outcomes has to be equal to 1. Or in shorter notation, P sub 1 plus up to P sub j plus up to P sub m is equal to 1. Now we often use a little x instead of j as an index, And the little x here is in association with the capital X. So if we have x associated with S, then we would have O1 to O sub little x up to O sub m. And now we can develop a function notation. The probability that capital X is equal to the outcome O sub x is written as P of x. And then P of 1 plus up to P of x plus up to P of m is equal to 1. Now when we write the probability that x's outcome x is little p of x, then P of x is called the probability distribution of capital X. We can visualize probability distributions using histograms. So we can visualize P of x as a horizontal bar chart in which P of x is the area of the bar over x. So for a Faraday, all the bars would have an area of a sixth. If we had 1, 2, 3 twice as likely as 3, 4, 5, I'm sorry, that should be 4, 5, 6, then we would have 2 nights as the areas over 1, 2, 3, and 1 nights as the areas over 4, 5, 6. And this is our histogram. These are relative frequencies that we're measuring, and these are bins. Now, a uniform probability distribution means that all the probabilities are the same. So if there's little n outcomes, then the probability is 1 over n. Fair tends to mean uniform. And random number generators, which we'll see often in this course, are designed to produce uniform probability distributions. And then other distributions can be constructed from uniform distributions. Numerical random variables are very important because often x is associated with a set of outcomes that are numerical, which we are denoting here with the t. And these t1 to tx to tm are numbers, t being the numerical tag of this outcome. Now, little p of x, the probability x is the number, t sub x. And if we let x randomly take a value in S, our sample space, then P of x is the probability we'll choose the number T sub x. And we call this x taking a random value a sample. Now if we perform n independent samples, now what do we mean independent? Well, that means every time we choose a number from S, every number is in there. So if we picked T sub x last time, then we would put it back in before taking the next sample. Or in other words, we'll call this sampling with replacement. So T sub x occurs approximately P of x times n times. T1 occurs P1 of n times, T2 P2 of n times. And we can now compute the average value of over the t's over the n samples. So let E sub n of x be the average over n samples. For n large, we'll call it the sample mean. And it could look something like this. We may have gotten a T3, and then a T5, then a T2, then another T2, then a T sub m, so on and so forth. Or we could have gotten something like that. Regardless, we know we'll eventually write it in this form, where we put all the T1s at the beginning, the T2s next, so on and so forth. And we know that we'll have about P1 of n times the T1 will occur, and P2 of n times the T2 will occur, and so on. And this is approximately, it's not exact. But if we write this approximation, then you'll notice there's an n in each one of these terms. That n factors out and cancels. And now we have that the sample mean, E sub n of x, for large n is approximately the same as the expected value of x, which is T1 probability of 1 plus T2 times probability of 2 all the way up to T sub m times probability of m. Now the same thing can be done with a function. If f is defined for all values in S, then for large number n of samples of x, we'll take the average of f of x, and the law of large numbers says that E sub n of f of x for large n is approximately the same as the expected value, f of t1 p1 plus f of 2 t p2, so on up to f of t sub m p sub m. So if mu, for instance, is the expected value of x, then an example of this is the variance of x, which is the expected value of x minus mu squared. And sigma here is the square root of the variance, is called the standard deviation. Now we often use more than one variable. We might roll two dice simultaneously. X would be the outcome of the first, y is the outcome of the second. Square on a chessboard chosen at random from row X and column Y. Two cards chosen from a deck of cards. X is the first, Y is the second. First and last names of a person selected at random. X is the first name, Y is the second. And the notation changes slightly. Each outcome now has two indices. So we would say that capital X is in 1 to m sub x and capital Y is in 1 to m sub y. And then the probability that x is I and y is j is the probability that outcome O sub ij occurs. Once again, we'll use lowercase x and y so that we're indexing by little x, little y. And then we have the probability of capital X being little x and capital Y being little y being the probability that O sub xy occurs. And we can write again this in function notation, p of little x, y, the indices corresponding to that probabilities. We call this a joint probability distribution. Now, when we say p of x comma y is probably x is x and y is y, it means that x takes on the outcome O sub little x and y takes on the outcome O sub little y at the same time. And simultaneously, or at the same time, means in the same trial. So let's look at an example. Suppose we've got me on one side of the planet and Dr. U is on the other. We both flip fair coins. X is my outcome, Y is U's outcome. We have four possibilities: tails, tails, heads, tails, tails, heads, heads, heads. A trial looks something like that. I might get a heads and you might get a tails. Each outcome is equally likely, so the probability in each case is 1/4. Or in function notation, p of 1, 0 is equal to 1/4. Marginal probabilities, given a joint probability, is just the probability of the x or the y individually. And to obtain those, the probability sub capital X of little x is just the sum over the y's of the joint probability. And likewise, the marginal probability of y is the sum over the joint probability over the x's. For example, suppose I've got a coin with a probability of heads equal to 1/4. So my coin probability is 1/4. Y is U's fair coin. Me and you are on opposite sides of the planet, so safe to assume that you and I are independent. So an outcome is a pair XY, where X is either heads or tails and Y is either heads or tails. And now we both flip our coins n times. I have heads in about 1/4 of the outcome pairs, and about 1/2 of the n over 4 outcomes which I have heads. U also has heads, so there are n over 8 heads pairs. So the probability x is heads and y is heads is the limit as n goes to infinity, n over 8 over n, which is 1/8. So likewise, we'll get the probability x is heads, y is tails is also 1/8. Now, what about if I get tails? In other words, pairs of the form tails heads or tails tails. In about 3/4 of the outcome pairs, I have tails. In about 1/2 of the 3/4 outcome pairs, which I have tails, Dr. U also has tails. So 3/8 of the n outcomes, me and you both have tails. So P of 0, 0 is 3/8, and similarly P of 0, 1 is 3/8. So what about the marginal probabilities? Well, it's no surprise, P sub x of 0, the sum over the two possibilities for Dr. U, and that's 3/8 plus 3/8 is 3/4. The probability of heads for me is the sum over the probabilities of heads for me and tails for you, and heads for me and heads for you, 1/8 plus 1/8, and that's a fourth. And similarly for the probability of 0 tails for Dr. U, the probability is a half, and the probability of heads is also a half. Now, me and you flipped our coins independently, and notice that if I have 3/4 times 1/2, then I get 3/8. In other words, P of xy is the marginal of x times the marginal of y for all outcomes xy. You can see 0, 0, that's 3/4 times a half. That's marginal of sub x of 0, and the marginal of x, marginal sub y of 0. Same thing happens. We always get the joint probabilities, the product of the marginals. And we'll see that random variables are independent if and only if the joint probability is the product of the marginals for all possible outcome pairs. Let's get another example. Jane chooses 3 cards numbered 0, 1, and 2. John chooses a card from the 2 remaining. X is Jane's card and Y is John's card. There are the possible outcomes. Notice that they never have the same cards. The probability of each one of these outcomes is a 1/6, and of course the probability that they each get the same card is 0. So what is the marginal probability? Well, we add the sum of the marginals, and that's 0 plus a 6 plus a 6, and that's a third. So John has a 1 out of 3 chance of picking the 0 card. No surprise there. And we get the same thing for picking the 1 card or the 2 card. Jane was picking first. John now picks, he's the Y, and notice that he has a probability of 1/3 of getting a 0, and likewise 1/3 for getting a 1 or a 2. So in summary, in joint probability there's often more than one variable. A joint distribution, P of xy, the probability x is x and y is y, simultaneously means the same trial, and we have the function notation. We have marginal probabilities. We have P of xy is equal to this product of the marginals if and only if the capital XY are independent. And one thing to notice is a lot of this is notation. So you'll need to learn what the symbols mean.